Hey everyone, welcome back to Calculus 2. This will be lecture 16 of the course, and in this session we're going to discuss integration by parts. And so this is a new integration technique that will be especially useful when integrating products of functions. And so this will be a key tool in your integration toolbox here. So let's go ahead and jump into it. And so we'll call this section 3.2, integration by parts. All right, let me double check that I'm focused here. Looks pretty good. Okay. All right, so so as I said, this is a new integration technique. It's based on the product rule from differentiation. This technique is based on the product rule from differentiation, as we'll see in a second. Okay, and it's going to be very useful when integrating functions that are, consist of a product of functions. So things like the integral of x times the natural log of x, or maybe the integral of e to the x times x squared, or trig functions and the exponential function, things like this. See, things where you have a product of two functions, two or more functions. Okay, so these types of functions are going to be dealt with handily by this integration by parts technique. Okay, so let's talk through what this thing is based on and how and what it's all about. So let's first recall the product rule. Okay, so we had the product rule. So basically the product rule said, hey, if we want to take the derivative of two functions u and v, then that's just going to be equal to u times the derivative of v plus v times the derivative of u. All right, so that was the simple product rule from differentiation back in Calculus 1, one of the first really important, super important differentiation rules we talked through. Okay, so the product rule goes like that. And so then, sometimes it's nice to rewrite this as u times v prime plus v times u prime. Okay, so that's just, and here u and v are, they're both differentiable functions of x, as you can see, obviously. But I'll write it down just to be sure. Okay. So that just means that the derivative with respect to x exists for both u and v. Okay. So if we start with this, d dx of uv equals u dv dx plus v du dx. If we start with that, and if I integrate both sides, what happens? All right, so integrate everything with respect to x. Okay, so this here is just uv. Right, now what happens over here? So remember, we're differentiating with respect to x. This would be dv dx dx. Right, so integrating this with respect to x, and then here we're also integrating with respect to x. Okay, and you can kind of see what happens here. Oops. These should be arrows, not, there we go. So I've got uv equals, now what happens here? This becomes the integral of u dv, and this becomes the integral of v du. Okay, and so this is kind of the natural, so if you starting with the product rule and then integrating everything with respect to x, this is what you end up with. Okay, and this is basically what integration by parts is all about. So, it's going to be this thing here, but with a slightly rewritten, right? So what we're gonna write this as the integral of u dv is equal to these other two pieces. So rewriting, we'll have the integral of u times dv is equal to u times v minus this part. Okay, and this is the formula for integration by parts. Okay, so I know that on the surface this doesn't seem like it would be very helpful. So I want to know the integral of whatever u is with respect to v, then I have to multiply u times v minus another integral. Well, the key to this this integration technique is the choice that you make for u and v, right? So in particular, this piece here, this integral of v times du, v du, is likely to be easier to evaluate than this integral, the integral of u times dv. But in order for that to be the case, u and dv have to be chosen very carefully. Okay, so just high level, we're given an integral that's a product like this. What we want to do then is we want to look at this product and assign some portion of the x ln dx to the u function, and some portion of it, the remaining portion, to the dv function. Okay, and so when we're looking at an integral like this, we have to make a choice. A choice has to be made about what's going to be the u and what's going to be the dv. All right, and then the whole integration technique kind of spins off based on that. So if we were integrating this one, we would have to say, okay, well, maybe we'll set the u equal to x and then let natural log of x dx be the dv. Or maybe we'll let the natural log of x be the u and we'll let x dx be the dv. Right, depending on your initial choice, you'll have more or less success. Similarly over here, if this was our integral that we were trying to tackle, we would have to assign some part of it to be u. So maybe we say e to the x is u, and maybe the remainder would be dv, x squared dx. We'll set that equal to dv. It's a substitution game, right? So the question is, when is it advantageous to assign something to u, and when is it advantageous to assign something to dv? Right, so there's some guidelines that we have to consider, right? And we'll do examples in a moment, but it's kind of important just kind of get these ideas out ahead of it. And they may not make a ton of sense absent the examples, but we'll be able to reference them. Okay, so here's kind of the guidelines. Here's sort of how you might want to go about choosing u and vd. Guidelines for choosing u and dv. Okay, so it's typically advantageous to let dv be the most complicated portion of the integrand that can be integrated. Okay, that you know how to integrate. So let dv be the most complicated part of the integrand that can be integrated. That obviously being the important thing there, that can be integrated. Right, so it doesn't make much sense to set dv equal to the portion of the integrand that would be hard to integrate that in fact you don't know how to integrate. You want to set dv equal to the most complicated part of the integrand that you know how to deal with. Okay, and then u will be the remaining part. Okay, so that's one guideline. That this guideline is kind of dictated by your choice of dv, right? U is just the remainder. Now, a second guideline would be to be very conscientious about your choice of u instead. So in this case, what you would say is let's go ahead and choose u to be the portion of the integrand whose derivative is simpler. And we'll talk about what we mean by that in a second. Let u be the portion of the integrand probably a better way to say it would be let u be the portion of the integrand that becomes simpler upon differentiation. Okay, and then of course dv will be the remaining part. I know this is all very abstract yet. Well, as soon as we do an example, we'll see. Okay, so two basic guiding sort of principles when you in your selection of u and dv. First of all, if there's an obvious part of the integrand that is complicated to integrate, if there's a complicated part of the integrand that you know how to integrate, that's always a good choice for dv, and let the rest be u. If there's a portion of the integrand that you know how to differentiate, and when you differentiate it, it becomes a simpler function, that's a good choice for u, and let the rest of the thing be dv. Right, so an example here would be like x squared is typically a good choice for u, because the derivative of x squared is 2x, so it becomes simpler. It's no longer a squared variable, it's just x to the first power. Right, something any integrable function that takes up a significant portion of the integrand would be a good choice for dv. Right. Okay, let's see an example here of this kind of selection of u and dv. Okay, so let's talk through an example. let's consider this one. So consider the integral of x times e to the x dx. Okay, so a product of x and e to the x, so this is a good candidate for integration by parts. So here's like the options. There are multiple options here for our choice of u and dv. So first of all, we could do this, where we've got x times e to the x dx, right? And we could say, let's let x be the u, and let's let e to the x dx be the dv. That's one option. Okay, another option would be to say, let's let e to the x be one piece and the other piece be x dx. Right, so let's let this be the u, and let's let this be the dv. Okay, that's another option. There are a couple more, right? So another one would be, what if we let 1 be the u and x e to the x dx be the dv? I mean, that's just another way to break it up. And then I guess finally, probably the last way you can do it. I mean, there are probably lots of ways you could algebraically manipulate this thing to break it up differently, but a good place to stop would be with this one. What about x times e to the x as the u, and then simply dx as the dv? Okay. Now, so each of these, you'd have to consider, but there's a clear best choice, right? So this one is obviously not a good choice. Like, we don't even know how to we do not know how to integrate this piece of it. It's certainly the most complicated part of the integrand. It's the whole thing, but we don't know how to integrate it, right? So this one is definitely out. This choice here. Now, what happens when I differentiate this u? If I differentiate this, does it become simpler? No, it becomes quite a bit more complex, actually. You'd have to use the product rule for derivatives, and it would be x times the derivative of e to the x plus e to the x times derivative. Like, it would be more complicated. So this one is out. So these are both violations. This is a violation of principle 1, letting dv be the most complicated part that you can actually integrate. We can't integrate that. This is a violation of principle 2, because this becomes more complicated when you differentiate it. So you don't want to do that. What about up here? Well, we can certainly integrate this choice of dv, and we can certainly differentiate this choice of e to the x. Right? So this one is an option. This one is the same, right? We can certainly integrate e to the x, and we can differentiate x. Now, there's a better, one of these is better than the other. Which one is better than the other? Right, well, this one is the best, right? And the reason is because it kind of fits both guidelines, right? On the one hand, we can definitely integrate e to the x dx, right? That's on the one hand. So that's the complicated part of the integral, relatively speaking, that we know how to integrate. And also, it is also a good fit for principle 2, because if we differentiate x, it just becomes 1, right? So this becomes simpler upon differentiation, right? So this one over here wouldn't be a terrible choice by any means. These would both be terrible choices. This would be an all right choice, and it might work, but this is the best choice because of the x becoming simpler. Okay, and so that's what we would do. We would assign u to be x and dv to be e to the x dx. Okay, now let's walk through what happens then when we make that choice. Let me just flip to another sheet so I have plenty of space. Okay, so we've got the integral of x times e to the x dx. And so what we're going to do is we're going to let u equal x, and we're going to let dv equal e to the x dx, right? So this is going to be our substitution choice. And so what we then have to do is we have to calculate du, and we also have to calculate v, right? So if u is equal to x, then du is equal to 1 times dx. Okay? And if dv is equal to e to the x dx, then v will be equal to the integral of e to the x dx, which is just e to the x. Okay, don't worry about the constant. Constant's not important for this piece of the calculation. Right, so here's our substitutions. We've got a u, we've got a du, we've got a dv, and we've got a v. So now what we want to do is we just want to follow the formula. Right, so remember the formula for integration by parts is the integral of u dv is equal to u times v minus the integral of v du. Okay, so let's plug all these pieces in here. So obviously the integral of u dv, that's what we started with. This is the u, and this is the dv. So we've got the integral of x e to the x dx is equal to, now what's u? Well, we chose u to be x. And what's v? We find that v is equal to the integral of e to the x dx, which is just e to the x. Okay, then minus the integral of v times du. So v is e to the x, and du is dx. Okay, so you can see here this is the integral u dv, which is the complicated integral, and by our choice of u and dv, we have derived a v du that is this one, which is obviously very easy. Okay, and so we can quickly calculate the rest of the integral as x e to the x minus e to the x plus c. Okay, that's how integration by parts works. Okay, that is the idea. All right, so you choose a u and you choose a dv, and you choose them according to these principles that u needs to become simpler upon differentiation, and dv needs to be something you know how to easily integrate. Not necessarily easily, but hopefully easily. Right? dv needs to be integrable. You need to be able to do it. You need to know, you need to be able to apply an integration rule or some sort of method. Okay? And then from those two choices, you derive du and v, and everything gets plugged into this expression here. This is the central expression to recall from integration by parts. Excellent. Okay, let's try another example. If you do a few examples, the pattern here becomes pretty clear. What about this integral? X squared times the natural log of x dx. Okay, so there's a number of ways to do this, and I recommend trying different ways and seeing what happens when you try this in using different techniques. So the way I'm going to do it is I'm going to let u equal the natural log of x, right? And that means my dv is x squared dx. I think this would probably work if you chose u equal to x squared and dv equal to the natural log of x. You'd have to check that. But let's try it this way. So if u is natural log of x, then du is equal to, right, 1 over x dx. And if dv is equal to x squared dx, then v is equal to that integral, which is x to the third power over 3. Okay, now let's see what happens here. So remember, the integral of u dv is equal to u times v minus the integral of v du. Okay, so let's plug everything in. So u dv, of course, is our starting integral. And u we found to be the natural log of x, or we chose anyways. And then v would be x cubed over 3. Okay, and then minus the integral of v, which is x cubed over 3, du. Now du is 1 over x dx. Okay, so then we can see that this integral is going to be something we can handle, right? Because there's going to be a cancellation. It'll basically be integrating x squared. Okay, and so we can move on to the next level here, and I'm going to rearrange some of these as we go through. And so I'm going to pull the 1/3 out, and then this is x cubed over x, so it's just x squared, right, like so. And that means we've got x cubed over 3 times the natural log of x minus 1/3, and then what does this become? Well, that's x cubed over 3, isn't it? All right, and so that means the integral is x cubed over 3 times the natural log of x minus 1/9 x cubed plus c. Okay, excellent. So you can see that this is a very efficient way to go about things. This is very nice. Right, it lets you start with this, and you just have to make a wise choice on u dv. Now this is where, you know, kind of the old issue of integration being a little more of an art than a science. I mean that a little tongue-in-cheek, right? But you know, like, there's some trial and error that could potentially come into play. It may be the case that if you choose your u and dv in a particular way, it's not so good, and you may have to start over with a different selection. That's okay. All right, don't be afraid to just say, okay, forget it, start over, try something else. It's kind of the way it is with integrals. How about this one? This is a little more complicated one. Let's evaluate the integral of arcsine x. Okay, so we don't have an integration rule for the arcsine, but maybe integration by parts can help us. So in this case, let's let u equal arcsine, and of course that means dv is equal to just dx. Okay, so if u is arcsine, then du, well, we'll have to go back and reference some of our Calc 2 material on the derivatives of the inverse tangent, or the inverse trig functions. And what we would find, though, is that, okay, if u is arcsine, then the derivative of that is 1 over 1 minus x squared. All right, so not a derivative that necessarily looks simpler, but I think in principle this is easier to deal with than the arcsine when it comes to this stuff. So then v would be equal to the integral of dx, which is, of course, just x. Okay, and so here's our substitution. Let's see if this gets us anywhere. So remember, the integral of u dv equals uv minus the integral of v du. That's our formula. And so we've got the integral of arcsine x dx is equal to, now what's u? Arc sine x. And what's v? Just x. Okay, so it's that minus the integral of v du. Okay, so v is, again, the x, and du is this thing, 1 over the square root of 1 minus x squared dx. Okay, so we've got it all together here. Okay, very good. Now, let's see, is there some way to integrate this? Well, it turns out that there is. Right, so let's write this as x arc sine x minus the integral of x over the square root of 1 minus x squared dx. Okay, now we can use a u substitution here on this. And so the u sub would be u equals 1 minus x squared. Right, that's this little piece inside the radical. And then du is equal to negative 2x dx. Okay, so there's a u substitution we're going to have to plug in here. Okay, so let's see what happens here. We've got x arc sine x minus, and well, so we have the x dx, but we don't have the negative 2. We have the x dx. Actually, we have the negative x dx, but we don't have the 2. So we'll have to divide by 2, right? Multiply and divide by 2. And so this would actually become plus 1/2 times the integral of, and then this would be negative x dx here, right? So we kind of bring the negative inside, it's a plus. And so, and then this is just really u to the negative 1/2. So that's what we would do here. Just like so. And then this is easy to integrate, right? This one is easy to integrate. So we have x arc sine x plus 1/2 times, and then this would just be u to the 1/2 over 1/2. And our u, of course, is 1 minus x squared. Okay, so this would be 2 times the square root of 1 minus x squared. And we can clean up some of this a little bit more, like the 2's will cancel in particular. So we have x times the arc sine of x plus the square root of 1 minus x squared plus c. Okay. Right, so not an easy integral, but doable. And part of the way you would do this is through using this integration by parts, right? So a choice here that would maybe be hard to see maybe would be hard to see through to the end how this choice of u is going to play out. This would be an example where you're just going to have to try some stuff, right? When you try this, you do see that, oh, this is very doable. Although on the surface, this maybe looks worse, right? But if you've been practicing your integrals and you look at this, you might be able to say, oh, I can see a u substitution that'll work here, namely this 1 minus x squared. Okay, and that would get you through it. That would get you to the finish line. Excellent. Okay, now, so those were kind of, well, easier examples, right? Occasionally, you come across an example like this where you have to use integration by parts repeatedly. And that can happen. In fact, it's pretty common. I know that when I was in, doing integration regularly, this would come up fairly often. So let's evaluate the integral of x squared sine of x dx. Okay, so there's a couple of choices here that are kind of obvious. So let's let u equal the x squared and dv equals sine of x dx. Okay, so that means du is 2x dx, and that means v is the integral of sine x dx, which is negative cosine x. Okay, so here's your integration by parts. And so then we're going to plug that into the integral of u dv equals uv minus the integral of v du, right? So just repeating that as many times as possible so that people kind of get that built, drilled into your heads, right? So that means we've got the integral of x squared sine of x dx is equal to u times v, so that's x squared times negative cos x minus the integral of v du, negative cos x times 2x dx. Okay, let's go through here and kind of flush all of these signs together, right? So I've got, let's kind of clean it up. Is what I mean to say. Negative x squared cos x plus the integral of 2x cos x dx. Okay, and so we kind of got to this point. Now usually this integral here is really something we can easily deal with. It's usually a one-stepper. Maybe you have to do something like with a u substitution in the previous example, but here when we get to this point, we're kind of stuck again. We're sort of still we're in a similar position to where we were when we started. So we had x squared sine of x, now we have 2x cos x. So there's nothing we can do with this. There's no u substitution, there's no obvious integration rule that we can employ. So what we can do here is we can actually do integration by parts again, right? And the advantage in doing that, again, is that you'll notice that if we choose u to be equal to 2x, then du is just going to be a constant, right? And that's going to simplify the integral considerably. So if u is 2x, then dv is cos x dx. That means we've got a du of 2dx, and we've got a v, that's just the integral of cos x dx, which is equal to, of course, the sine of x. Okay, so here's our second integration by parts. What we're going to do is we're just going to plug the formula into this piece of the integrand. We're going to bring this along for the ride and then just expand this using the integration by parts. Okay, and so that means we've got x squared, negative x squared, cos x, plus, now this is the integral of u dv, right? And so it's going to be plus u times v, so 2x sine x, minus the integral of v du, which is going to be sine x times 2. Okay, so this is u times v minus the integral of v du. Okay, we've kind of just plugged all of this. Let me just make a note here. Into this. Right, this is our chosen u is 2x, that's that. Our chosen dv is cos x dx. So this is our integral of u dv, and it's equal to u times v minus the integral of v du. That's what this part is. And now we can see that, oh great, now it's just a constant times sine, so we can easily integrate this last integral. And so we get negative x squared cos x plus 2x sine x minus 2 times, now what's the integral of the sine? Well, the integral of sine is cosine, so this would just be cos x, okay, and then plus c. Perfect. And so that means that our initial integral was the integral of x squared sine of x dx, and we find that that is equal to negative x squared cos x plus 2x sine x minus 2 cosine x plus c. Okay, so kind of a longer problem, but yeah, like, so this idea, this integration by parts is extremely versatile, right? And so it can be repeatedly applied to the same integral. And basically, when you do that, what you're doing is you're kind of whittling down a part of the integrand that is troublesome. So this x squared upon the first integration by parts gets whittled down to a 2x. And then we do it again, and it gets whittled down to a 2, right? The dv part of it just keeps flipping from sine x to cosine x, and then back to sine x. And if we had to do it another time, it'd be back to cos x. But this other part gets steadily reduced until it's just a constant. And then that's how the integrand becomes simpler over time, over iterations as you iterate. Perfect. Great. Now there's another very interesting example that can come up when using integration by parts. So let's take a quick look at this example. This is one that I thought was pretty interesting when I first encountered it. Let's try to evaluate, this is an example, evaluate the integral of secant cubed x. So again, we don't have a good way to integrate this. There's obviously no integration rule that we can apply to this secant function. Certainly not the secant cubed function. So let's try integration by parts. Let's let u equal secant x. Okay, and then the rest of it, dv, let's let that equal the secant squared. Okay. Right, so secant cubed is obviously just secant times secant squared, and so we can kind of pull it apart into two pieces. Now the reason we would do that is because we do have an integral for secant squared, right? And so that means v is equal to the integral of secant squared x dx, which is the tangent of x. Okay, and then the derivative of u, du, would be equal to the derivative of secant, which is secant x tangent x dx. Okay, so here's our integration scheme. Let's see what happens. So if we start with the integral of secant cubed x dx, that's our u dv, then that's going to be equal to u times v, which would be secant times tangent, minus the integral of v du. So v is tangent, and du is this, secant x tangent x dx. Okay. And let's clean this up a little bit. So we get secant x tangent x minus the integral of secant x tan squared x dx. Okay. And this may not look great, but look what happens here. We can pull out some trigonometry. And so instead of the tangent, we can use Pythagorean identity to write secant squared x minus 1. So I'll just put that over here. Note that tan squared equals secant squared minus 1, right? This is the lesser known of the Pythagorean identities. Okay, so just recalling your trigonometry there. And so that means this can be rewritten as secant x times secant squared x minus 1 dx. Okay, and it may seem like we're sort of circling a lot, so we're not really getting anywhere, but let's see what happens if we expand this one more time. So secant x tangent of x minus the integral of secant cubed x dx minus the integral of, it'd be plus the integral of secant x dx, right? So basically all I did here was distribute and then simultaneously sort of pull them into two separate integrals. So I have secant cubed x, so that's minus secant cubed x. That's this part, these two. And then this and this would be a negative secant x, and then it's minus, so it becomes plus secant x dx. And so you may be saying to yourself, hold on, you're telling me that the integral of secant cubed x dx is equal to this whole mess? Well, look at here. Look at what we have here. We have a portion of our integration by parts is equal to the original. That's sort of strange, isn't it? That's kind of the lovely little trick here, actually. So what we've done is, so this is a situation where if you just keep going, you're going to end up with more and more secants, more and more tangents. It's just going to kind of continue to grow and be harder and harder to deal with. But at a certain point, we've created a situation where a significant portion of the integration by parts section of the integral is actually captured by the original UDV choice. And so now what we can do is we can actually employ just some basic algebra. Okay, so basically I'm going to add this integral to both sides. I'm going to add the integral of secant cubed x dx to both sides. Another way to say that is I'm going to bring this to the other side of the equal sign. Right? And so what I end up with is over here I have 2 times the integral of secant cubed x dx is equal to this secant x tangent x plus this, the integral of secant x. Okay? All right, so I have this. Now, can I integrate this part? Yeah, this part I can definitely integrate. I know how to do this. All right, so let's do that. Let's see what happens here. I'm going to keep writing. No, I don't need to do that. So we'll just kind of continue with the chain here. So this will be secant x tangent x plus. Now, what is this one? This one is one you might have to dig in to some of the earlier stuff. But this turns out to be the natural log of the secant plus the tangent. Okay. And so I'm real close, right? Because I want to know what the integral of secant cubed x dx is, but I know what 2 times that integral is, right? This over here is 2 times the integral of secant cubed x dx. So can I just divide both sides by 2? Sure. Yep. That's what I'll do, right? We'll divide both sides by 2, and that gets us to the finish line. Right, so that means this whole thing divided by 2 is equal to our starting integral, our target integral. Right, so it'd be 1/2 secant x tangent x plus 1/2 natural log of secant x plus tangent x. Okay, so that is a great trick, right? Using integration by parts to spin up copies of the integral you're trying to integrate, and then using algebra to pull those pieces out, and that simplifies what you have to actually integrate, right? Because here we'd be basically back to square one, right? But if you recognize that this is exactly what we started with, you can bring it over here, increment this by from 1 to 2, and then you just have to integrate this piece, right? And so this part of it you don't end up having to worry about. Right, it's a fantastic little trick. I remember the first time I saw it, I was like, well, that is very clever. It kind of just sprung on me too. Like my teacher didn't point that one out to me when I was in calculus 2, and I remember coming across it on my own and thinking, is this legal? Can I do this? Of course you can do it. Definitely can do it. All right. Okay, so that's integration by parts. There's lots and lots of examples in textbooks. And there's lots of interesting ways that it comes up, and we'll use it more in later lectures as well. It's just going to be tossed into our sort of storehouse of integration techniques. But let's quickly kind of summarize a few things, right? Just the strategic things, right? So let's do a summary of common integrals that use integration by parts. right? So just kind of a summary here. Because the key to using integration by parts is knowing how to choose your u and your dv, right? So let's talk about some examples of what you might see. So what if you have, for integrals of the form, and this isn't an absolute guide, this is just something to give you to think about. If you have something like x to the n e to the ax, you know, something like that, or, you know, x to the n e sine of ax. Sorry, I started writing e there, and that's an s I n sine of ax. Or, you know, like x to the n cos ax, it's sort of the same thing. So things like this, where you've got basically an x to the n, and then you've got an e, you know, one of these functions which, when you integrate, it just kind of keeps flipping. Then a good choice for u is the x to the n, and the dv would be the rest. Okay, and that's because specifically here, your choice of u as x to the n is going to mean that the derivative is n x to the n minus 1. So it's going to keep dropping, you know, decreasing the power of that of this polynomial here, this term. Right, so that piece of it will become simpler every time you differentiate it. The rest of it's just going to keep flipping, right? The e to the when I integrate e to the ax, it's just going to be e to the ax again. When I integrate sine and cosine, same thing, right? It just keeps flipping. So there's nothing, and the same thing is true of the derivatives, right? So you'd get nowhere if you chose the other direction, right? If you let the e, sine, or the cos be your u, and the dv be the x, you're not going to get anywhere. Okay, so that's a good technique there. What about integrals like this? X to the n ln x dx, or x to the n arcsine, or like arctangent, x to the n arctan x, right? Integrals like this, what should we do? Well, in this case, the dv makes more sense as the x to the n. So let dv in this case be the x to the n, and we let u be the other part. Right, and the reason there is because when you let u equal natural log of x, it just becomes 1 over x. And when you let u become arcsine ax, right, it converts into like 1 over the square root of 1 plus x squared or something, right? You kind of get rid of the trig function, you get rid of the natural log function. Things kind of reduce down to more seemingly manageable, or you know, manageable functions, or functions where you're going to have more cancellation potential, or more opportunities for expansion or changing the integrand. Right, if you choose it the other direction, then first of all, some of these might be hard to integrate, and they might not be straightforward to integrate at all. And also, well, that would be the main thing. Your u would tend to decrease, that's true, but you'd get a little more juice for the squeeze, I think, if you let u be natural log, arcsine, or arctangent. Again, these are things you can experiment with, try different ways, and see what happens when you do it one way versus the other. And then finally, what about integrals like where both parts of the integral are, you know, like an e or a sine or something that kind of just keeps flipping? So what about integrals like e to the ax times sine of bx, or e to the ax times the cosine of bx, right? Something like this. Well, these are, you know, kind of instance by instance, but, you know, a good choice here would be to let u equal the sine of bx, or cosine of bx, and then let dv be the other one. right? And in these cases, a lot of times these will flip and you'll be able to, right? Because notice here, like when I differentiate the sine or the cosine, basically I'm just going to get a new combination. If I differentiate sine, I get cosine. If I differentiate cosine, I get sine, right? And similarly over here, as I'm integrating this, the integral of like e to the ax, I'm just going to get another e to the ax, right? So I think you can, what you'll end up probably seeing with these is that as you try integration by parts with things like this, you're going to end up with scenarios kind of like what we just saw with the secant cubed, where you might be able to represent significant portions of the integral as the original integral. You might be able to do some algebra and create opportunities to kind of get rid of the portion of the integral that you actually have to integrate. Okay, now these are tricky. They can be tricky, right? You just have to keep your wits about you as you're doing this. Just remember, all you have to do is remember integral of u dv equals uv minus integral of v du. Like that's the key, right? And then remember your choices of u and dv, right? Choose wisely your u and dv, and if something seems like it's just making it worse, maybe go back to scratch and restart with a different selection. Okay. All right, so that is where I will leave it. That's integration by parts. And after, next time we get together, we'll talk about trigonometric integrals and just some interesting techniques that can be used to integrate functions that are composed primarily of trigonometric functions. So that'll be next time. We'll just continue down the path of getting more and more experience with different kinds of integrals. All right, see you then.